Welcome to the 2023 NORR program, and I hope it's a beautiful day wherever you are for this, the first day of spring. I'm Silvio Baldessera, Chair of NORR, founder of NORR, and your host. NORR is a continuing education program founded 16 years ago with three main goals: to teach, learn, improve, and to do that continuously. The program relies on bringing the best guest speakers in three series: architecture, engineering, and the masters. Each of the NORR virtual sessions since 2020 have been recorded and are available on NORR YouTube for global access. Welcome to the 14 NORR office staff and their invited guests. Welcome also to the students from the 14 schools of architecture from Canada, the US, and the UK. Net zero greenhouse gas emissions by 2050. How did we get here? This slide shows we started our industrial revolution in 1750, and the same time that Volta and Fardley advanced the practical use of electricity. Somewhere around 1870, we humans rapidly induced CO2 emissions, beginning without control until just recently. Finally, in 2010, we woke up and set 45% reductions for 2030 and net zero for 2050. We all know those are minimum targets, and we need, as architects and engineers, have an obligation to advocate in the built environment more than ever for the future generations. So how are we doing? Well, yesterday, the IPCC synthesis report after 8 years of research noted that we have reached 1.1 degree now. And if we do not accelerate reductions in greenhouse gas emissions, we will be at 1.5 in 2030 and higher in 2050, which is alarming. The UN Secretary General called on all nations to come together to meet the recommendations of the IPCC synthesis report. Key takeaways from the IPCC synthesis report on climate change are specifically outlined and worth reviewing and provide a path forward for governments and policymakers. Of the mitigation options outlined is solar energy, wind energy, and electrification of urban systems, which are technically viable and becoming increasingly cost-effective and are generally supported by the public. Our NORR session today on electrifying buildings brings this critical climate change architecture and engineering discussion presented by our guest speaker. Rachel Deradoorian-Beaudoin is a sustainability engineer with Bureau Veritas, where she leads project teams to deliver decarbonization strategies at a building and master plan scale. Her individual work focuses on sustainability, renewable energy planning, and building electrification. Her career has included work in real estate development, construction, and engineering, and lays a foundation for an integrated approach to decarbonization of the built environment. Rachel's work includes a number of US embassy projects internationally for the US State Department, a net zero carbon academic campus in Hawaii, and building scale projects at universities across the Midwest. She is a graduate of Northwestern University with a master's in energy and sustainability and a focus on energy markets and financing, and an alumnus of the University of Miami with a degree in architectural engineering. Welcome today to Rachel.
Thank you so much, Silvio. It's such a pleasure to be here. And I'm so enthused to be able to talk to you all today, eager to decarbonize the built environment with a conversation about all electric buildings and impacts on infrastructure. So looking forward to having a great discussion. I wanted to share a little bit about Bureau Happold in terms of the work that we do in this space. And really the conversation that's going to happen today is going to be centered around these three categories of projects. Some of those are all electric ready buildings, and we'll talk about what that means. Some are fully electric, all electric buildings and facilities across climate zones. And then the third category of projects that are really important are zero carbon master plans. And I think this is language that certainly everyone on this call is familiar with. But what I do also want to emphasize is we recognize that all electric buildings are just one component of a much larger climate action agenda. Notice the language climate action and not necessarily just climate change. But our belief at Bureau Happold and our belief as designers in the built environment more generally is that a clear path to decarbonized buildings and a decarbonized built environment is all electric buildings connected to electrical grids supplied by renewable energy sources. So as we move through this conversation today, also just a nod to recognize that an all electric building design is only one of many components of creating a decarbonized built environment well into the future. So what we're going to talk about today is really divided within four categories as we develop goals for building electrification. The first, greenhouse gas emissions. Thank you to Silvio for bringing up the recent IPCC report on that as well. But the goal of building electrification is ultimately to eliminate operational carbon, eliminating operational greenhouse gas emissions from the built environment. We're going to talk a bit about grid resiliency, which is how buildings can be designed to actually be grid responsive and not simply demanding of the grid, noting that resiliency in the effects and in the wake of climate change is a really important conversation for us to have. The third and fourth category is technology and cost. We're not going to spend the most time there today in this conversation, but just know that technology continues to advance such that electrified buildings are possible and plausible across cold climates. I'm sat here in Chicago, but a lot of this work has been and the analysis has been conducted in cold climates and warm for comparative states. And last but not least, we're going to talk a bit about cost, really just emphasizing that all electric buildings are cost competitive, and we'll dig into what that looks like in just a little bit. But the moral of the story is the question we're kind of here to answer today is, what's the feasibility of all electric buildings across climate zones and sectors? As someone who's a proud Midwesterner, this is near and dear to the work that I've done across the Midwest and certainly top of mind in terms of importance. So we're really going to dig into that and lean into that today. The analysis that's going to be presented in this report, in this conversation, had the following study parameters. So we studied 5 locations, as you can note, Detroit, New York City, and Boston being the coldest climates. And we recognize that there are colder climates in Canada, and we can talk about what that might look like in practice. And we also studied San Francisco and Los Angeles as well. We studied 4 sectors, so you'll see these repeated throughout some of the results and conversation we're going to have. We studied multifamily residential, office, laboratory with humidification, which we'll talk about as more of a niche component, but science and tech does make up a large part of the Bureau Happold building portfolio, and higher education. We studied 3 envelope systems, a ASHRAE 90.1 2010 envelope, which is basically congruent with LEED version 4, if that's helpful as a reference. ASHRAE 90.1 2019, so what we're seeing as reference of stretch code, it's what's IECC 2021 is based on. And then a high performance envelope, which is basically triple pane glazing, a super, super effective high performance envelope, one that exceeds code and in all intents and purposes. We studied 3 different forms of domestic hot water, condensing boiler. So this is fossil fuel paired with fossil fuel HVAC systems. We'll talk about what those look like, but these are natural gas based systems. Electric resistance. So what that is a 100% efficient electric resistance heating coil. Heat pumps, which will be a large component of the technology section when we get there. We studied 4 HVAC systems, 1 baseline fossil fuel fan coil unit system, so 4-pipe system, as I'm sure most of you are familiar, and then 3 fully electrified systems ranging from heat pump technology to just a straight up heat recovery chiller paired with a cooling tower. And then there were many constants across some of these study parameters that we did, but most importantly, wanted to keep internal gains constant so we can have a conversation really about what an all electric building looks like in its relationship to the grid. Just a few key terms. HVAC system 1 is a water-cooled centrifugal chiller with a condensing gas boiler. So straight up fan coil unit system. We've got a water-cooled chiller with a heat pump chiller with air source heat pumps as supplemental heating. We have an air source VRF system with heat recovery that we studied, and then a water source VRF system with heat recovery with electric resistance as a supplemental heat injection component. So let's start and really dive into greenhouse gas emissions. Why are all electric buildings important off the bat? Well, I don't think this stat is going to be new to anyone on this call or anyone who's joined this profession, but buildings account for 40% of greenhouse gas emissions globally, which means basically it's time for the built environment to get a move on and really consider decarbonization as a key motive for everything we're doing in development for the next 30 years at a minimum until those 2050 goals are reached. And what we're going to talk about in this section are how we need to be paying attention to what's happening on the grid scale to assess and determine grid greenhouse gas emission factors that contribute to system selection and early design decisions. We're going to talk about high performance envelopes as a key contributor to decarbonization. We're going to talk about designing radically low energy systems. So ultimately, I know this is not going to be a surprise to anyone on this call, but the less energy a building uses through a fully electrified system, the better we are. And then we're going to talk about assessing long-term GHG emissions. How do you make a decision based on future policy and what the considerations are there? So although this is a US focused conversation, did just want to highlight that across the US, and certainly this is true globally, there's such a wide range of carbon factors in terms of what generating sources electricity is coming from in different regions of the country, in the United States, divided by states. And so what's really important to note about this is that these were based on 2018 values, but a lot of them still hold true, at least in similar ranges. The darker the color is on this slide, the more carbon intense that region of the grid is, meaning that if we look at this in bar chart format, there are three thresholds that we kind of use as rule of thumb in terms of when do we want to talk about full electrification. First is near term, right? Where are the physical locations where an all electric building makes carbon sense today, right? These are values that are current, and these are places that are emphasizing or relying on lower carbon generation sources for electricity. Some examples of this are highly renewable places, Vermont being one that has a almost neutral grid factor at this point in time. But some of these conversations become more complicated as we reach this kind of midterm. So lower GHG emissions should be studied with all electric buildings, but against the timeline of grid efforts. And so what's also mapped here is states or locations that have existing renewable portfolio standards or existing climate action plans, such that although electrification may not be carbon advantageous tomorrow, when we consider the long-term planning and the integrative resource planning and the utility engagement that's happening in these locations, it may be beneficial to create and develop an all-electric ready building, such that when the equipment and the MEP systems need to be turned over, we are prepared for a fully electric building that accommodates a future cleaner grid. So one example of this is what's happening in the state of Massachusetts right now. Back in 2021, Massachusetts climate bill basically dictated in law the year-over-year projection of renewables engaged on the grid. So pretty self-explanatory in terms of what's going on here, right? Policies dictating an increase in renewable energy being brought to the grid as a whole. And what we're seeing in turn is greenhouse gas emissions associated with the grid are continuing to anticipate to plummet, ultimately reaching zero approximately by year 2048. And what's important to note about this is that even if we might not have considered an all-electric building as carbon advantageous back in 2018, we can certainly recognize that for projects that are in design now that will likely be under construction or completed by 2030, that conversation is going to substantially change. So one of the first things we're going to talk about, which is the most simple term, but still the most important as we talk about greenhouse gas emissions, is energy efficiency. And what we've found through a lot of these studies, both against fossil fuel heating systems and electrified building systems, is within cold climates, designing and establishing high performance facades are one of the key components to reducing operational greenhouse gas emissions associated with both electrified and fossil fuel buildings. And what we've also noticed is that a high performance envelope paired with, and this again was based on our sensitivity energy modeling analysis, a high performance envelope paired with a heat pump chiller all electric system demonstrates the best energy performance in a cold climate. And what's really critical to note about that is that with the use of a heat pump chiller, again, this is a nod to technology that we'll talk about later in this session. But basically what's happening here is that when we are able to create a highly tight facade, we're able to rely less on individual system typology, therefore relying on simultaneous heating and cooling and other components that heat pump chiller systems are able to deliver. And what's also important to note is that when we look at straight up EUI, which I know is a component energy use intensity, a key factor that everyone is paying attention to already, when we look at straight up EUI across all sectors, comparing the fossil fuel base case fan coil unit scenario against the scenario of the heat pump chiller across all climate zones, an all electric heat pump chiller system is outperforming in terms of straight up EUI values the equivalent fossil fuel system, including but not limited to lab spaces, which are all often highly contentious in the all electric building discussion. And a few other things worth noting when we talk about how do you take potential future grid factors and potential future greenhouse gas emissions, why does that matter? Well, it matters because the buildings we design today are in operation at a minimum for 50 years on average. That's the lifespan that's studied within a real estate pro forma. So what's really critical to note about this is that although still with the fossil fuel scenario, there is of course electricity also associated with the chiller, right? So we do see reductions in greenhouse gas emissions year over year. This is again using Boston as an example against their grid policy and the law that's been signed. But what's most important to note is that fossil fuel related greenhouse gas emissions, because there is natural gas present, the scope 1 emissions associated with those buildings will never go away. However, in fully electric scenarios, based on policy and based on location, we can see completely eliminated greenhouse gas emissions for operational carbon associated with electric building systems and significant reductions even by 2030, which is effectively when buildings we're designing today will be open. And so just to show this across all scales and all sectors that we studied, basically, first and foremost, reducing the EUI of the building, designing buildings with high performance facades and focus there, we are able to achieve net neutral carbon emissions associated with electric buildings across most sectors by 2050, and even some by 2030 based on local or regional policy or utility guidance. So as we move from greenhouse gas emissions to the grid, there's two really critical factors that we've noticed. Number one is reducing peak heating load requirements, right? I'm certain everyone on this call is familiar, for those of you who have worked in cold climates for a while, and certainly the electrical engineers on my team are always bringing this up as a key point of order, which is electrical connectivity and electrical system infrastructure is typically designed to match the peak cooling load requirements of a building. Now, what's really important to note about that, when we look at grid resiliency, when we look at grid connectivity to the building, making sure that we are reducing peak heating load from electricity for all electric buildings is really critical to not overburdening our electrical grids, recognizing that heating is a life safety issue. Cooling is not in the same vein a life safety issue. The second critical thing we're going to talk about are demand management strategies. I think for a long time, there's always been kind of an undercurrent rhetoric that states that the grid will provide whatever the building requires. And I think what we're recognizing, certainly in locations that are being directly impacted by climate change, is that we actually need to do a better job as designers of designing buildings that are responsive to the grid and not just dictating the requirements. So what we're going to talk about here is managing peak loads. How do you do that? One of those ways is going to be a facade, and we'll talk about that in just a moment. Understanding demands. So what does it mean to actually shift all of your heating to an electric source? Implementing demand management, and then a brief discussion about avoiding peak demand times, talking a bit about time of use and carbon intensive grid sources. So one of the things we wanted to use for the managing peak electrical loads in conversation was a residential study for for multifamily residential. And the most critical takeaway from all our analysis, and again, this analysis was performed across all 5 of those building sectors. Boston's just some of the most extreme temperatures lately, so we've been using that as the basis. A high performance envelope at a minimum has the largest impact on reducing peak heating load required. And the other thing worth noting is that the peak heating input, again, this is measured in kilowatts. So in terms of actual demand requirements, we are able to actually significantly reduce the peak heating input required from fossil fuel to electric in terms of total kilowatt hours required. And what's more important about this is we look at this at a seasonal scale, recognizing that peak cooling requirements also continue to get hotter in the effect of climate change, and design temperatures continue to be adjusted in order to accommodate more extreme weather events, is that as we're able to maintain the peak heating load requirements in kB2 per hour and keep that below the peak cooling, we're able to effectively manage our relationship to the grid. So basically saying, as we continue to design buildings, maintaining the peak heating load below that requirement of peak cooling is our best bet. And so what does that look like? That looks like that's different for all different scenarios, right? In all different sectors. In a residential application, we're really able to recognize that demonstrating peak cooling exceeding peak heating is possible for all scenarios amongst these. The complexity also falls in lab buildings. And we know that lab design is more specific, incredibly performance-based. And so in a lab scenario, we also are recognizing that peak heating does at times exceed the peak cooling requirements. And although this is not necessarily a non-negotiable for grid connectivity and grid coordination, what we do know is that this is incredibly building type specific, and maintaining those conversations with grid operators, understanding what else can be done in terms of demand management strategies to support all electric lab buildings or all electric ready lab buildings is a really critical conversation. So to talk a bit about what this looks like across cold and warm climates, I'm certain this is not a lot of surprise that Los Angeles and San Francisco, as an example, rarely have situations where the peak heating load is greater than that of peak cooling, but we also do see that pretty often in Boston and Detroit. And so what's really critical to understand there is that as we look at minimum temperature requirements, Detroit's minimum temperature design being -4 and Boston's minimum being -1, that's really where we're seeing the differential between peak heating and peak cooling. And again, this is not a non-negotiable conversation, but it simply means that demand management strategies are more necessary in cold climates. And so let's talk about what those demand management strategies might be. So the 6 that we've got up on the screen are really just kind of conversation topics and important conversations to have within the early design phases of a project. Some of those include flattening the curve. So how can we utilize better use of simultaneous heating and cooling based building systems to help flatten the curve? How do we use things like price, time of use pricing, or time of use price avoidance to really drive that conversation home? Because not only is this enabling for a lower carbon operational building, but this is also potentially enabling cost savings, operational and utility cost savings. Some of the other really low-hanging fruit design strategies are adaptive thermal comfort and system zoning. System zoning is especially imperative for those of you who have worked in science and tech before or do a lot of lab design, but recognizing where flexibility can be maintained in terms of adaptive thermal comfort or temperature set points, and where it can't, because there will always be cases where that's not a possibility. A few other conversations to have are thermal storage. That's certainly a possibility for a lot of district system connectivity and other locations where we may have excess heat and may be able to create thermal storage or a thermal network that supports the reduction of peak heating demands. And then controls and process loads. So again, this can be specific to lab or office settings, most likely, but recognizing that careful management of process loads, or those unregulated loads as they're defined by ASHRAE, is a really critical component to reducing the peak load as well. And just to talk a bit about demand management briefly, but Some of those benefits that I briefly discussed in terms of avoiding peak times on the grid or avoiding those time of use rates, there's also greenhouse gas emissions benefits associated with those. So what's shown here on the screen is basically a 24-hour profile of 5 cities that we've done work in. So in accordance with the electrical utility that was provided for each of these sample projects. Also recognizing that there is not only potential cost avoidance by not operating at peak times on the grid, but there's also potential cost penalties from not obliging. So San Francisco is a great example of that. There's actually a demand management penalty associated with not being able to reduce your load on the grid during times of necessity or during peak times. So with that in mind, let's talk about some of the technologies available to help support an all-electric building and to have it be one that is grid responsive and high performance as well. So what technologies are available? Heat pump technologies are really going to be critical. And I know there's been a lot of conversation happening within the built environment community recently as of heat pump technologies. And we're going to talk about busting some of those myths with heat pumps in cold climates here momentarily. Heat recovery, again, not a new conversation, but certainly one that's imperative in cold climates and where we have ability to kind of transition and minimize those peak heating loads. And then envelope performance, which we'll talk about as well. So some of those key considerations include space heating and domestic hot water, of course, being traditionally natural gas-based systems, but recognizing that those are what we're prioritizing for electrification. Heat pump technology, the other really key takeaway of this conversation is we're not encouraging just the use of electric resistance coils for heating. That doesn't really give us an efficiency advantage, although they are 100% efficient. We also know that electricity the costs are higher than that of natural gas, and that's really important to consider as well. And then we're going to talk about options for backup. You know, as I mentioned previously, and what's top of mind for a lot of designers, heating is a life safety issue. So as we consider what the options are for emergency backup or supplemental heating where needed, that's going to be really important. And then we're going to talk just briefly about the benefits of non-combustion based systems. I'm certain most people on this call are familiar with the International Living Future Institute Living Building Challenge. You know, so this is what's most applicable to those non-combustion based systems. So one really critical thing to note here is that as we talk about heating technology, we also want to make sure we're understanding the greenhouse gas emissions per unit of heat generated, because ultimately that's our focus here. So what's mapped out on the screen is a condensing boiler, so a standard run-of-the-mill fossil fuel natural gas boiler, operating at a 95% efficiency, which works, right? It has worked in the past, it works in cold climates. It's resilient in a lot of ways, and we'll talk about what that term really means when we talk about fossil fuel in a moment. But it's kind of standard run-of-the-mill baseline design, if you're okay with me calling it that. The other thing we've got here is an electric resistance heating. So at 98% efficient, this is an all-electric option, but as we also know, electricity versus natural gas has a cost differential. So that's why this is not our preferred option. However, as we look at this time frame, moving end over end, you know, from 2020 to 2050, which is what we've got mapped here, we are still seeing carbon reductions associated with an electric resistance heating based on those grid factors that as we've talked about. But most importantly, our recommended option here as we look at this across the board is a heat pump operating at a 3.0 COP. And we'll talk about what it takes to get a heat pump to operate at a 3.0 COP really quickly. But the moral of the story is that as we reduce our energy dependency, we are immediately reducing our ability below that of a fossil fuel condensing boiler baseline. We're reducing our greenhouse gas emissions ultimately to zero, but faster than a condensing boiler ever could. So heat pump technology, just a very brief introduction overview for those of you who are not familiar. But the moral of the story is heat pumps are electric-based equipment that exchange thermal energy with ground, water, or air. So a great example of that, geothermal, is a ground source heat pump, for lack of a better description. And what's really critical about this is that heat pumps are able to recover heat and simultaneously heat and cool and exchange that thermal energy, which gives them about 3 to 4 times the energy output of what's energy input from the grid. And so what's really important to note about this, and this map here on the right is a little bit funky, but bear with me, we're going to talk through it. Because in our studies, it's not best recommended to recommend technologies that are not going to be feasible within the locations that the buildings are actually going to be operational. And one example of that, and the constant pushback and conversations we have are, well, heat pumps don't work in cold climates. Well, in order to respond to that, we did a very in-depth weather analysis where we looked at ASHRAE, both heating design day temperatures and hours of the year, and wanted to understand how many hours of the year are we able to actually feasibly use heat pumps at a 3.0 COP or higher. And what we found is across all of these climate zones from Boston, Detroit, New York City, San Francisco, and Los Angeles, the percentages listed here at the top of the chart are the percent of heating hours where COP is at or above 3.0. And it's no surprise that for San Francisco and Los Angeles, those are 100% of the time. But what's also critical to note is Detroit, which has the most extreme heating design day temperature. Even then, 68% of total operational hours are at a 3.0 COP or above. And so what's really important to note here is that ultimately, our ability to operate at 3.0 COP or higher is really indicative of the fact that greenhouse gas emissions can be reduced in thirds, if you want to consider it that way. And so as we talk about redundancy and resiliency, because we do recognize there is a delta, right? If Detroit's sitting at 68% of total heating degree days in which it's able to operate at a 3.0 COP or higher, there are also needs for backup power solutions. Some of those things are going to be maintained as fossil fuel for the time being. That's not to say that's not going to change in the future, but I do also want to clarify, as per our definition of all electric buildings, emergency backup is not yet included. So fossil fuel generators and natural gas generators or even diesel generators are available for that. A few other things worth noting is the use of backup boilers if and as needed. So those could be natural gas-based or electric resistance-based boilers. And again, as this is serving as the redundant heating system, we don't want to rely on electric resistance as the key component, but as the redundant backup system where air source heat pumps may be challenged in the coldest temperatures. This would help also manage and ensure resiliency through design. Battery systems, again, top of mind for most designers in the built environment right now, paired with microgrids as well, but understanding that dynamically controlled buildings, abilities for buildings to self-manage their own loads, to have battery backup, whether on-site renewables are present or not, are really important components of creating a resilient building design. And also just a nod to alternative technologies as well that are continuing to be developed and continuing to have conversations within the built environment. Photovoltaics, everyone is familiar at this point in time. Solar thermal as well, right? Just a nod to the fact that on-site produced renewable energy or on-site produced hot water without the use of either fossil fuel or electric sources are immediately a reduction in the operational greenhouse gas emissions of a building. Wind technology, again, not as widely used as a building scale application for obvious reason, but understanding that campus scale, power purchase agreement, procurement of wind, and just broader development, certainly across the Midwest, for anyone who's sat here, is a really critical component to achieving those state renewable portfolio standards and ultimately achieving an all-electric building paired with renewable grid. Geothermal technologies, again, not new technologies, but really important use of heat pumps. Thermal mass, and most importantly, another unique one, low GWP refrigerant. As we're talking about heat pump-based systems, VRF-based systems, heat pump chillers, the conversations happening right now about refrigerants, their involvement in embodied carbon, and their involvement in the whole life carbon of a development, which is not the topic of today's conversation, but they're really important to understand that cooling systems also have a really critical role to play in embodied carbon. And then just a nod to why non-combustion buildings, ultimately an all-electric building is non-combustion, are crucially important to public health and the just transition to a decarbonized built environment as well, is that combustion emissions from the US building sector contribute to the largest share of premature deaths associated with air pollution. And so there's been a lot of studies recently from RMI, MIT, and even some more recent ones that have indicated that cooking combustion for indoor air quality and indoor environmental quality has had a really critically poor impact on human health. And outdoor air quality, I think the state of California is a great example of this, with finally having to issue this year outdoor air quality warnings. There's really, really critical conversations we need to have about promoting all electric buildings and non-combustion alternative technologies to support human health and well-being, because ultimately our job as designers in the built environment is to support the people that live and work there. And so we're going to wrap up this conversation today with a discussion about cost. And what's most important to recognize here, I'm not a cost consultant, I'm not a construction manager, but I can tell you I've been a member and a party to many value engineering discussions, as I'm sure we've all had. But the really critical takeaway here is all electric buildings are becoming increasingly cost competitive. And a nod to that includes, but is not limited to, the advancement of technologies and the manufacturer engagement in climate action, as we noted in the last technology section. It's also a nod to the fact that prioritization is happening at both a federal scale with the recent Inflation Reduction Act, as well as at a local scale with opt-in stretch codes and similar conversations, that all electric buildings are becoming cost competitive. And a few key cost factors that we're going to talk about today include space planning. A lot of conversations happening about heat pumps include, well, heat pumps just are going to be hundreds of modules on my roof. We'll talk about what that actually might look like through an example of a laboratory in Boston. Capital cost, utility cost, and potential carbon penalties. So certainly everyone who's familiar with Local Law 97 in New York as a really pilot policy for what's happening for carbon penalties, we'll talk about what that looks like as well. So from a space planning perspective, we know as designers, leasable area, an area that is revenue generating, is the most important component of space planning in a building, right? More times than not. We also understand that life cycle costs really contribute to what's happening now. And as we're seeing more and more developers asking for that as top, climate emergency, climate action becomes top of mind, as well as preparedness for emergency systems and emergency conversations, life cycle costs are becoming increasingly crucial for a long-term outlook and for, honestly, risk management in any kind of real estate or design portfolio. Cost of implementation. So we'll talk just a very briefly about capital cost implications. And then we'll very briefly wrap up with engaging in the market, which is to understand that power purchase agreements, market-based risk avoidance strategies, and driving competition for that are really critical foundations. So what's important to note here, and this is a space planning example for a Boston office, between our baseline fossil fuel scenario and the fully electrified scenario here. And so what's important to note between these two left sides, the gray over here is what does not change between the two space planning examples. What's important to note is the air handling unit sizes don't change, the building core does not change. And then these other areas, so alternate auxiliary equipment, etc. What does change is really just kind of a redistribution of space from air source heat pumps, cooling towers, and generators. And what's most important to note here is that we're actually able to save about, through this space planning example, again, every building is different here, but this is just to show it can be done. We were actually able to save about 11% and dedicate 11% more to tenant amenities than versus a fossil fuel baseline scenario. For a lab example, this looks a bit different, but ultimately what's happening here is a bit of reduction for the tenant amenity spaces, but still it's not incomparable. So what's again important to note, building core and air handling unit pump, exhaust fans, none of these really critical components of space are changing, but there's a bit of redistribution because instead of utilizing cooling towers and having a lot of cooling towers, air source heat pumps are used in lieu of them. And instead of very large footprint required for maglev centrifugal chillers, we're actually able to kind of split up that space between centrifugal chillers and a heat pump chiller as well. Another quick conversation that I'm certain architects will have something to discuss here, because this is always a topic of contention, but envelope capital cost, right? I'm certain a lot of you, when I was discussing the importance of a high performance envelope, you're all nodding along to say, yes, we know that. We've been told this a million times. But what's really critically important is that as we look at increasingly strict code requirements for energy code, as we're looking at opt-in stretch code or even mandatory zero codes that are happening in municipalities across the country, Boston and New York City certainly being two of them, we're recognizing that the cost differential between double and triple glazing, just to use this as an example, and this is data pulled from 3 different project cost estimates, the delta is somewhere between 10 and 17% on average cost add. We understand and we recognize that is a cost add, and in certain cases, an add is not appropriate in any means. However, as we begin to look at this from a systems perspective, the additional costs for all electric ready or fully electrified system options, the cost add per square foot in terms of the total costs for mechanical and electrical systems is much lower as a total percentage basis. And it's also completely dependent on, of course, on building program and size, backup power solutions, as well as all electric versus all electric ready options. Again, tying this back to the importance of life cycle costing as well, even though there are marginal but present cost adds associated with all electric system designs and higher performance envelope systems, what's really critically important to understand is that we want to make sure that just because a condensing boiler may be selected as a basis of design or as a first cost system, when we're looking at the actual greenhouse gas emissions associated with it and the dollars per MMBTU, meaning utility costs, our heat pump systems are becoming more cost competitive. And the other thing worth noting here, again, to reemphasize this, our recommendation for all electric building systems are not just electric resistance heating, because typically when system options are presented, electric resistance heatings is the default that people's minds go to. And they say, well, why would I want that? Because when we're looking at this graph as an example, the cost per MMBTU is immense for that system type. But when we look at the heat pump, there's pretty close cost comparison. And when we pair this with potential market engagement, which we'll talk about just in a moment, it can be even more cost competitive. So incentives and penalties, let's look at the New York City Local Law 97 example, which is, again, not dissimilar and certainly a conversation that I know has been across USGBC, AIA 2030. It's been top of mind since the policy was rolled out just a few years ago. And so the moral of the story is this policy dictates maximum carbon budgets per building type and per either existing or new buildings. And so as a part of this study that was conducted for all electric buildings, we wanted to understand where the median existing construction in New York City sits and where each of those system options that we deployed and that we modeled would sit against those carbon budgets. And what we realized is utilizing fully electric systems are one of the most important ways to align with and to actually be able to comply with future local law 97 policy. Because the way the policy is written, there's only going to be increasingly strict and stringent carbon budgets applied. So this orange line here, using the lab as an example, is the 2024 to 2029 local law 97 carbon emissions cap. But as we get to 2030, the purple line establishes a much more aggressive carbon budget as well. So what's clear to note now is that as we think about the prospect of all electric ready buildings, that becomes a very necessary conversation to have in order to assure and demonstrate compliance against future laws, including but not limited to Local Law 97. And just a nod to this before we close out this part of the presentation here, a bit on market engagement and energy procurement. So going back to the original reflection as a part of the climate action agenda, right? All electric buildings connected to grids supplied by renewable energy resources enable zero carbon buildings. And the connected to renewable grids part, as we talked about in the greenhouse gas emissions and the physical location of a lot of these facilities, buildings, and projects that are active, what's happening is a market shift conversation that's encouraging the definition of zero to not just mean based on what your utility provides, but to actually enable owners, project developers, designers, politicians, all of those individuals to ensure that renewable energy doesn't just have to come from on-site renewables. And there are market engagement opportunities. Of course, on-site renewables is a great example, but community renewable energy is now enabled in several states across the US. Power purchase agreements, whether virtual or physical, and then renewable energy investment funds that are becoming increasingly wider available across different municipalities across the country. And so another thing to note there is that this becomes a broader portfolio management conversation for clients. This becomes a conversation that is much more geared toward broader decarbonization principles and broader investment in climate action. But that's ultimately what a conversation about an all-electric building does. So just to close this out, when we talk about the feasibility of all-electric buildings across climate zones and sectors, we've established a very brief checklist, a feasibility checklist, if you will, for all electric buildings that I hope everyone can take to their next conversations and really start to have these conversations early in design to establish priorities for decarbonized built environment. So for greenhouse gas emissions, reducing energy use intensity, energy efficiency, again, not a new concept, certainly not something that designers are unprepared for. But recognizing high performance envelopes are a crucial step to get there, especially when we talk about the relationship to the grid. Selecting efficient all electric or all electric ready systems as a baseline, recognizing that there are opportunities for improved system performance with all electric system design, and evaluating local grid carbon factors and lifetime greenhouse gas emissions as well. So paying attention to the policy that exists, paying attention to what the policy leads to, and recognizing that there is a decision to be made between all electric now, all electric ready, and what that preparedness needs to look like as well. Under grid resiliency, managing and reducing peak loads, particularly in cold climates, right? Making sure that you're paying attention to the needs of your building in relationship to the grid. So reducing those heating loads below the cooling load requirements, again, back to those high performance envelopes. And then prioritizing reliability and resiliency by developing a grid interactive building. So that's going to look different for every single location. That's going to look different based on your utility provider. That's going to look different based on the cost incentives, the time of use pricing, all of those things. But paying attention to those demand management strategies and enabling your building to be an asset and not just a standalone entity that does not support broader grid resiliency is important. Under technology, maximizing the use of heat pumps, right? Studying those in location to the specific climate zone that you're in, recognizing that there are conversations to be had and there are opportunities for advancement and better system efficiency in those conversations. Relying on fossil fuel generators where necessary, but recognizing that as an emergency power source. And then eliminating on-site combustion ultimately. So identifying that there are health, equity, and just transition conversations to be had about eliminating on-site combustion for buildings. And then under cost, implementing cost competitive full electric systems, encouraging teams to study what the cost differential actually looks like and studying that not just on a CapEx basis, but looking at the life cycle cost available there. Also using financial hedging strategies. PPAs are a great example of that. Having conversations with utility providers, green tariffs, all of those conversations can ultimately contribute to more effective carbon sources for your electricity and for your fuel types on your site, but also potential financial hedging and risk assessment strategies as well. And then the last thing, again, just to encourage this for all designers today, study the life cycle costs, include carbon as a part of your life cycle costs. It's now a necessary component of a basis of design for a local law 97 building, as an example, but utilizing that as a basis for potential future policy and not allowing projects to be dead in the water because of carbon penalties before they even get a chance to exist. And so with that, I'd love to say thank you all very much for listening, and I will hand it back over to Silvio to start our panel discussion.
Rachel, thank you. That was informative. It was comprehensive, and I think you're right on time. And I think I learned more in your short presentation than I've learned in sitting through 3 or 4 hour presentations. Thank you for that. This conversation is a timely one, and it's one for not only architects but mechanical, electrical, and structural engineers, and it's for the entire community. It's for government leaders, it's for our developers, it's for virtually everyone that's on the line, including our students. We're actually really happy to have 3 distinguished panelists today, and I'd like all 3 of them to turn on the cameras as I introduce them one at a time. And I'm going to start off with someone that represents government, and it's Ram Narayanamurthy. And he is the Deputy Director of the Building Technologies Office at the U.S. Department of Energy, Office of Energy Efficiency and Renewable Energy. He joined the DOE in 2020. Prior to the DOE, he led the Electric Power Research Institute's building program, which focused on large-scale development of decarbonization strategies in existing and new buildings. The program's notable accomplishments include the first production-built zero-energy community, decarbonized solutions for retrofits in affordable housing communities and smart energy communities. Ram has also extensively worked with state organizations, including California Energy Commission, the New York State Energy Research and Development Authority, cities, large home builders, affordable housing developers, HVAC manufacturers, and utilities to scale emerging technologies and to advance building decarbonization. Prior to EPRI, Ram focused on innovation and product development at ICE Energy and EcoFirst. As the Director of Product Development for ICE Energy, his teams developed ICE Bear, one of the first packaged thermal energy storage systems for light commercial buildings. He holds 27 patents across a breadth of building technology, including HVAC, water heating, solar, and controls technology. Ram holds a master's degree in mechanical engineering from Pennsylvania State University and a bachelor's degree in mechanical engineering from Indian Institute of Technology. Welcome, Ram. Our next panelist is Lindsay Baxter, who is the Manager of Regulatory and Clean Energy Strategy for Duchesne's Light Company, DLC, in Pittsburgh, Pennsylvania. Prior to joining DLC in 2018, she was a program manager and Pennsylvania Environmental Council, where she worked with diverse stakeholders to advance clean energy policy and programs. She has also worked in local government in the sustainability coordinator for the city of Pittsburgh. She holds a master's and bachelor's degree in environmental science. And our third panelist is Blake Jackson. He is an architect and director of sustainability for NORR. He has 22 years experience in the AEC industry and holds a Bachelor of Architecture degree from Kenshaw State University in Marietta, Georgia, and a Master of Architecture and Sustainability in environmental design from Architectural Association Graduate School in London, England. He currently serves on the advisory board for the University of Massachusetts Dartmouth's interior design program, and from 2016 to 2018, he was elected on the board of the Boston Society of Architects as their vice president of advocacy in 2021. He was named a lead fellow by the U.S. Green Building Council for his accomplishments in promoting green buildings. Welcome to all three of you. We are happy to have all three of you on. Ram, if you could turn on your camera, if that's possible. And I'd like to open this discussion, if we can, with perhaps Ram, you asking a few questions of Rachel on her presentation.
Hi, Sylvia.
Ram is still at the moment and should be back shortly. So,
okay, all right. So why don't we move to Lindsay?
Sure. Thanks for having me. I always forget that I should go through the phonetic pronunciation of our company name whenever we do the prep calls. So I'm with Duquesne Light. Also sometimes known as Duquesne, Duchesne. No, it's always like a fun when you wear your name tag to conferences, having people guess how to say the name of your company. But I'm with Duquesne Light Company in Pittsburgh, Pennsylvania. I'll just give like a few very brief remarks on sort of the electric utility perspective on what we've discussed today. And then I'm looking forward to the Q&A and conversation. But just to level set, Pennsylvania is a deregulated state. So our company, like all other electric companies in the state, we do not own generation. So we are agnostic to some of the things that were talked about today, like on-site generation or community renewables, PPAs. We see ourselves really as an enabler of helping our customers get to where they want to go in terms of this clean energy transition. So briefly, the reason that Rachel and I connected is our company is in the process of building out some programming around beneficial electrification. And the way that we define BE is electrification of an end use that results in overall energy savings. So our customers might end up using more electricity, but we need to make sure that they're saving overall. And then closely related to that, beneficial electrification needs to result in cost savings, as well as reductions in environmental impacts. So principally emissions, but also some of those health and safety factors within the building itself. Like a lot of electric utilities, initially that work has been focused more on the transportation electrification sector. So we have some robust programming in that area. We've done some projects with customers offering rebates on charger installation, really focused on public charging, working with our Port Authority on electrifying part of their bus fleet, things that are going to lead to wider benefits for our service territory. But probably of more interest to you, actually, I guess I should say that we do offer also a time of use rate to EV drivers. It's the only time of use product we have today, but I can see in the future potentially expanding that to other use types. So closely aligned to some of what Rachel covered about how do you incentivize demand management and leveling out that load curve. We're in the process right now of assessing the, I guess for lack of a better term, market potential of some of these electrification technologies in our service territory, understanding what is the most technically feasible today, what's the most cost effective, who are our customers that are most likely to start adopting these technologies, who are the customers that maybe aren't the most likely but would benefit the most. So we do have widespread access to natural gas in this part of the state, which can sometimes make the cost economics challenging on some of these projects. But we certainly have customers who are using electric heating today. Some of those may be heat pumps. Some of those are certainly less efficient options. We also have some customers in the more rural parts of our service territory that are on propane or other delivered fuels that might be initial early adopters. And so that's kind of where we are today. We don't have like, I can't talk about programs we have today, but I was encouraged to see the slides that Rachel shared about the emissions associated with grid electricity in various parts of the country. I know we have folks on here from all over, but Pittsburgh is, kind of part of the Appalachian region of the United States, certainly, very close to coal country. I'm a daughter of a coal miner, so, something that's like near and dear to home. And there's a misconception that most of the electricity in our area is coal-fired generation. Certainly that would have been true, 20, 30 years ago. Especially in the last 10, 15 years, we've really seen this rapid transformation and associated with that, a drop in emissions associated with grid electricity. Now, giving credit where credit's due, a lot of that has come from fuel switching from coal to natural gas. So certainly when we talk about clean energy, we're thinking more about things like nuclear and renewables and zero carbon fuels, but natural gas has been a very important part of that transition, at least in our region. And we do see probably a mid-long-term future where we still will be using natural gas in the generation fleet. But I think that probably is a better use of that resource where you have it in an efficient, centralized power plant where emissions can be measured, managed, accounted for, as compared to, using in potentially leaky or less efficient distribution systems and on-site combustion in people's homes and buildings. I think Rachel did a really nice job of talking about, grid impacts, load management. That is a piece of what we're looking at today. So while we're thinking about what customer programs and education and things like that we might offer, I'm more on the policy side of the house, but certainly I have my colleagues on more of the technical and engineering side of the house that are looking very closely at how robust is the grid, how resilient is the grid, will we be there to serve our customers in an electrified future. One of the things that's unique about our service territory, anybody who knows Pittsburgh is familiar with its very industrial past, and we certainly still have some heavy industry, but not as much as we did at one point. So the good piece of that is that we have extra capacity on a lot of parts of our grid, but we certainly, have areas where it's more aged, it's more constrained. So looking at pinpointing where infrastructure investments may be needed, and then thinking about, on the customer side, where the customer may need to upgrade their equipment in order to electrify, what are the costs of that? And is there a role that the utility can play in helping to remove some of those barriers? Yeah, I think that kind of covers like my introductory remarks. I'll just say, it sometimes feels a little bit like we're building the airplane while we're flying it, looking at the regulatory and legislative piece of it, looking at the rate making piece of it, looking at the customer programs and the grid side. So we're very focused on partnership with our customers, with businesses, with local government. That's certainly how Rachel and I got connected, and really appreciate the panel today bringing more light to these issues. Looking forward to the conversation.
Yeah, and I would just add to that, Lindsay, to that nod to collaboration and coordination. Certainly the work that you and I have been able to do together is a great example of that. But I think we need to remember as designers to humanize utilities a bit. And I know that's been true in the work that we've done for fully electric buildings. A lot of these things, Boston, for example, there's a lot of grid congestion issues that are currently happening right there. And Lindsay, as you and I have discussed, capacity is not the same issue that we have in Boston as we have in Pittsburgh right now. But I think just encouraging the conversation and recognizing that we as designers do have an ability, and we owe it to ourselves in the design of these eventual projects, to coordinate effectively and to coordinate proactively with the utility providers. So that's my other piece of encouragement, Lindsay, that you shared.
Thanks, Lindsay. Why don't we move over to Blake?
All right. Thank you for actually not making me go last, because I was afraid everybody was going to get to my comments before I had a chance. So this is really fantastic. So first off, I just want to say congratulations on a fantastic presentation. I want to echo Silvio's comments that it was rich, it was dense without being complicated. It was interesting, it was engaging, and for an hour, there was a ton packed into that of value for a broad audience of stakeholders. So congratulations to you and your team for a fantastic, informative, engaging presentation. Some comments from my end, and just sort of in the role that I'm in, both as with NORR and in my previous work with another large Canadian-based multinational company. I get to see a lot of market activity in various different countries, in particular where we're located right now, which is the US, Canada, and the UK, all of which happen to be cold climates, minus our outpost in Sacramento, but it's in California, so it's sort of a forward-reaching office in and of itself in its own right. I've been in Boston, although we don't have a Boston for for NORR, I do work remotely for them, as well as am housed in our Detroit office. So it's really nice and convenient for this study just to see those numbers brought in from those two particular climates, because I can speak to a lot of the work there, in particular Boston, because I've been located there now for over 13 years. And the largest part of my work was compliance with BERDO and compliance with the BPDA's Article 37, which is their version of Local Law 97. And all of the conversations, particularly both for commercial buildings as well as multifamily residential, was around this conversation of grid electrification, building electrification, transit-oriented developments, and zero waste systems, which is really sort of the combination of factors that represent the greenhouse gas emissions of Boston and its attempt to decarbonize by 2050. What's encouraging about your presentation is that multiple entities in the United States, which this was a United States-based presentation, are all going to be able to decarbonize by 2050, which is a longer timeline than what we have in our Canadian scenarios, which is 2040, or our UK scenarios, which are 2030 to 2035, depending on where you're located. So in those scenarios, the decarbonization and building electrification conversation becomes more cost effective and more of a driver for projects than they do in a United States-based scenario, which this presentation was based upon. So I think that that's very encouraging to see that in these other countries that tend to be a little bit quicker to act with regard to climate policy, both carrot and stick of climate policy, there's a business case here where it's going to unfold the slowest. One of the challenges that that I encountered, and I look forward to having a discussion with you about this later, in those conversations is overcoming the initial cost, because you do have to go to a bank or a series of investors. And even though we're being forced now to think about the whole life of the building, which finally we're being forced to do this, there is still the reality of the moment in time that we're battling with our clients for competitive fees and the act of design and construction today. And one of the challenges that we're running into is with that 82% number that you showed for Boston. Well, the clients automatically, because they're all generally quite clever, come back and say, well, what about the other 18% of the time? And their options are not great, because the options are essentially doubling up on systems for that redundancy for when we're less than 1 degrees Fahrenheit, which happens fairly frequently despite global warming, and a loss of leasable space, which you did acknowledge that was the most important aspect of the project and is the functional reason for the building to exist in the first place. And the options are that they'll have to purchase the technologies, lock them into place over time, and then change them out before the end of their useful life. And that's a bitter pill to swallow for a lot of clients. And so I'm interested in learning a little bit more about how you're overcoming that, in particular for the housing component, just because that's the area where this is perfect for. And Local Law 97 and the BPDA's Article 37 and various different other similar entities across the globe are essentially pushing for all electric passive houses. And it gets difficult to, passive house is a program that's been around in Germany and from Germany and other alpine climates for 40 years now. But it's based on a high level of predictability and also not necessarily zero combustion fossil fuels on site. And so these are some of the challenges that we're running into with sort of cost overruns and complexity and And again, the initial act of design and construction, which is predicated upon being competitive now with the long-term promise that may or may not be recouped by the investors, those are really the challenges, but it's encouraging to see that we're finding ways around it with also the promise that the grid is following through on its covenant to electrify and to decarbonize, which that's always been a bit of a variable. And the fact that technology is getting better and more easily usable, and also codes are increasing to a point to where this is all happening simultaneously. So, two final thoughts, and I know that was a lot packed into a few minutes of conversation, but two final thoughts from other countries that maybe the U.S. could learn some lessons from. In Canada, I've seen a commercial building that was fully electrified, and it's a net positive carbon project. It's 104,000 square feet, a project called Evolve One in Waterloo, Ontario. And how they were able to accomplish that feat on a commercial building is that the landlords actually did a green lease where they built to suit. And because they controlled everything in the build to suit, they also were able to enforce the budgets for lighting and ventilation and other various different metrics. The building was also LEED Platinum certified. It was fully electric, all on site, utilized ground source heat pumps, et cetera. But beyond that is this notion about engagement and responsibility for the use. And you said something pretty valuable in your presentation, is that the expectation has always been that you'll walk over and there'll always be as much power as you want to use. And the reality may be very different in the future, is that we have to get a little bit more creative and accountable for the energy use that we have in the buildings. That is already happening in the United Kingdom right now. And I'm working with a team who is giving me reports back. I'm not physically on the project, but I'm really curious to learn about this, because in Scotland, in order to receive funding for school projects, one has to guarantee an energy performance level. And based on the performance level, the percentage of the funding follows. And to me, that is such a great idea and such a difficult thing to manage, because we aren't necessarily in the architecture and engineering side in the business of managing engagement of the users. And we can predict energy use and carbon emissions and all these things during that moment of design and construction. But to hand over the building and to ensure that it is working optimally for the users is a totally another, that's a whole other universe out there that we've yet to really crack the code of that. And so I thought it was interesting and also risky that they are tying actual performance to ongoing funding. So it's not just one and done, it's an ongoing engagement. And the fact that it's happening in Scotland means that it will happen in England very soon, and then it will happen in Canada very soon thereafter, and then eventually it will come to the US. So I think there's a lot of opportunity for us to learn as an industry from this ongoing conversation around engagement, which is really the whole missing link of the piece, is that people fundamentally don't understand their accountability for their energy use and their footprints, and that can now change in a pretty profound way. And we're starting to see legislation to reinforce that. And again, I'm curious about your thoughts, but overall, very, very informative presentation. And thank you again for accepting our invite.
Absolutely. And Blake, I think I want to start with the first question you asked, because I have other thoughts on kind of risk and the role that it plays both operationally and financially as well. But to answer your first question about, capital cost still is the baseline, right? A lot of developers, certainly multifamily residential is a great example of that. To take a step back, one of the critical conversations we're having right now with owners is operational resiliency. The state of California is a great example of this. Several clients that we're working with there are concerned about operational resiliency. They're concerned about redundancy of systems, and they're actually becoming more willing, again, this is client dependent, becoming more willing to invest more upfront if we can tell the story of potential cost penalties if operational resiliency and if operational continuity is not maintained. That's just one part of the story. I think it's more critical to office and lab, and even higher ed in certain cases than it is to multifamily residential. But I think helping to quantify what potential interruptions might look like from a cost basis is really important. A great example of that is working on a laboratory project here in the Midwest at a higher education institute. Actually, they've asked us to help us quantify, okay, if research projects have to come offline because we lose power, or they have to come offline because we have an interruption of service, what is the actual dollar value associated with that service interruption? Which could be quite large, right? It could involve, in the nature of a research institution, a start over of experiments. It could involve months or days or weeks of lost work. So that's just one component, is actually supporting and assigning a monetary value to lost operations is certainly one way that we're trying to have that conversation. Because when you put that value up against a capital cost, could be meaningful or it could not be, right? Could go either way, depending on the client and the nature of the project. Residential is a really unique application and a really unique part, I think, Blake, to your point, because we know that we know that we want to provide safe housing, right? Like any developer that wants to develop housing, the human focus is really at the center of that. In terms of having those capital cost conversations there, some of those things are happening at the pro forma level. Again, this is entirely client dependent, but some of the conversations we're having are to say, look, if you're able to filter through, recognizing that clients will have lower utility costs, right? Your renters, occupants of the building will have lower utility costs as a result of this, they may be willing to pay more in rent. And again, this is a client dependent conversation, but trying to kind of explore the value, recognizing the audience and recognizing the building occupants, or even recognizing, we've had a few developers recently say, hey, look, we want to actually include utility cost as a part of rent because we want to be able to impact and we want to be able to design a really highly effective building at a minimum to be code compliant, like you said, Blake. I think that's the other thing happening now. Developers are now realizing that a code baseline building, and I think this is true designers too, a code baseline building is no longer just an easy toss away design, right? With codes like Birdo in Boston, with codes like Local 187 in New York City, it's becoming increasingly difficult. So recognizing either you have the funds to do a project that meets code or you don't. So I think having that conversation and inviting the conversation of all electric buildings sooner on, is going to allow for the conversation to go no-go sooner.
Yeah.
I don't think that's a perfect example. Every client's going to have a different response, but for two key pieces of advice there, number one, quantify the need for operational resiliency and operational continuity. And then two, recognize and understand where else in the client's portfolio or the pro forma use policy, right, to help support those conversations to get these over the finish line where needed.
The thing that's great about this conversation as well is the real driver behind all of this, or at least the way I see it, maybe this is the way an architect looks at this, is that we're really trying to maximize the architectural part of the building. I mean, the whole conversation is predicated upon, particularly for these cold climates, better envelope, which in my mind sounds like more percentage of the budget going towards the thing that I love the most, that lasts the longest on the project. And it's not the technology, it's the physical infrastructure of the building itself. And therein lies the opportunity and the challenge. And on this note, we've talked a little bit about the premise of new construction, right? It's sort of, we haven't said that this is a conversation about new construction, but I'm suddenly reminded of a project I was working on that was historically designated, or as we call in Canada, a heritage building. And we couldn't alter the envelope. And yet it's the existing buildings, particularly in these older cities like Boston, in Montreal, other places, that got us in the carbon conundrum in the first place. So in a scenario where you can't alter the envelope, what happens? Because I've seen the electrification at all costs conversation play out, and unfortunately it kills housing projects or whatever happens to go. It's too easy to make what should be a housing project in an old, beautiful, historic building that's integrated within a community become an office lab because of the economics of that scenario. So which will use more energy and needs even more air tightness that it won't get from historic envelopes. So what do you do in a scenario like that?
You know, adaptive reuse is something, those are my favorite projects I've worked on, to be quite quite transparent with this audience. But you're absolutely right. Adaptive reuse really opens the can of worms to much more complex conversations related to system design, system retrofit, all of those types of scenarios. One of the things that within our approach to zero carbon buildings, if we can reframe toward that conversation, is kind of evaluating the risk, and not just the risk of like, okay, if we do this, is there an economic risk associated with it, right? Is this going to become a sunk cost if we're designing an all electric ready system, or if we're doing a full system replacement for an adaptive reuse building? But there's also the risk, which is becoming more and more evident. As you said, like Europe is a great example of this, and their leadership that has been demonstrated in the broader carbon conversations. There's also a risk to not doing something at this point in time, right? If we look at some of the projects we're working on in Europe, a lot of which are adaptive reuse, a lot of those conversations are a risk to not complying against the EU taxonomy system, right? There's now a reputation risk for a client associated with not doing the right thing in the eyes of climate anymore. You know, with most major corporations that are clients of ours or clients of NORR as well, you know, there's a much larger client-based risk that they have to evaluate as well. So I think maybe this is an example, or maybe my potential proposed solution to this, which is not one size fits all, is like reframing the conversation to actually recognize like, hey, you're the owner, you purchased this building. Let's say it's on the National Register of Historic Places, you want to retrofit it, you're looking at system design options. Okay, well, do you want to design a building that has a lifespan of 10 years? Because as a developer, you're just going to flip it at that point in time. Or are you going to be the owner operator and you want to invest in this building, recognizing that it's going to be in your portfolio through 2050, at which point in time, guess what? Likely we're going to have close to zero grids. So a part of it also becomes the reputation risk and what the client themselves are willing to gamble in that scenario. Are they willing to gamble and say, look, this building is not going to be ours, or this building, we don't care about its performance, or we don't care that much about reprogramming? Or are you going to say, look, we want this to be a really important part of our portfolio from an ESG perspective, or from an EU taxonomy perspective, or from just an operational perspective as well?
Thanks for that, Rachel. Maybe we'll just move on to Ram has joined us, and Ram, your comments and thoughts about Rachel's presentation. You're on mute.
So
Perfect.
thank you, Silvio. And it was a great presentation. I enjoyed it. And I also had the chance to review it beforehand. So that gives me more time to think about it, right? So yeah, you're right. I mean, it's one of those things where I think a lot of us are, when we think about, so I'll go a little bit, spend a couple of minutes on what we are working through at the Department of Energy, right? We are thinking about what is our pathway to decarbonization. As we think about those pathways, we realize that it's going to be a confluence of energy efficiency, building electrification, maybe non-electrification options for decarbonization, and how do you actually integrate with that zero carbon grid. So Rachel, I really liked how you looked at the peak power loads in the buildings, because that's going to be a big driver for what happens on the grid infrastructure. So as we think about this whole electrification journey, both for transportation and buildings, one of the concerns is that if we don't do the efficiency, especially envelope efficiency, we will end up with a grid that's going to be much larger than it needs to be, because your peak loads are going to be higher, which means that you're going to be building bigger transformers, bigger wires, bigger switches, bigger substations, bigger transmission, bigger renewable generation, right? So it reframes the conversation around efficiency. And I also like the fact that you put in that emphasis on envelopes, because what it also does is that when we think about the utility side, they think of their assets as 50-year-old assets. I think, Blake, you raised the same issue, right? Which is, if we are going to map and match with that all renewable grid or a zero carbon grid, let's call it a zero carbon grid, then you need to make sure that the buildings are also having that same type of lifetime and life frames as the grid. And so that's where the importance of having a really good envelope comes in, because I think that underlines how you actually plan for the future system, right? So having said that, right, and I really like the framing of how you put together, how you went through, right, going from what drives GHG, the electrification, what it means to building peak loads, and how it actually interacts and provides customer benefits. Now the question is, have you looked at the energy costs for these buildings in different parts of the country? One of the challenges we run into is that when the electric rates are high, for example, in the Northeastern US or California, the energy cost could be a challenge. So how did you guys do the analysis when you did that?
It's a great question. So back in the cost section, which I know the slides will be available through the recording that will be posted eventually, but what we did study is we recognized, of course, that there are locations where the cost of natural gas and the cost of electricity are basically closer to one another, right? Which does form a lot of those results. The other thing that we looked at was basically, is there potential for market engagement? You know, through green tariff engagement, through PPAs, through community solar subscription, all of those things we found are effective financial hedges to reduce the actual cost of electricity, grid electricity. So that's one thing. The other thing is, we also recognize that we don't necessarily want to incentivize, you know, a electric resistance based system in Boston, where electricity costs are, like, check my math here, 27 cents a kilowatt hour or similar. So, you know, our recommendation is not a less efficient system where we understand the operational cost would be higher due to the cost of electricity. You know, our recommendation is design a more effective, more efficient system in those locations as well. But Ram, to your point, that's certainly a consideration. It's worth doing the life cycle against, right? And as much as I'm not a financial analyst, recognizing that price variation does exist, the price of utility electricity will likely be different 30 years from now than it is today. And, you know, when we look at the LCOEs and the levelized cost of energy for different renewable, non-renewable, traditional generating sources, renewable continues to decrease. So I will only take that as a somewhat good indicator of what we can expect in the future from renewable electricity generation sources.
Okay. And that's useful, right? I mean, so when you have customers who are able to kind of buy their own renewables, right, then it can start making economic sense. And I think that's something that is a challenge to work through. There's rate issues, there's all these things that utilities have to work through on their side too, because for the customers who don't have, who are buying utility power, that's something that we'll have to work on. The other question I had is, do you have operational experience from these heat pumps? How have they worked? I'm sitting in a building right now, which is all electric. It's in Spokane, which is pretty decently cold climate. And one of the challenges they had is that they went into a heat recovery chiller. And it was supposed to be operating on heat pumps with large thermal storage year round. And then the heat pumps are not operating really well below 20 degrees Fahrenheit, which means that they had to bring in electric boilers to do the backup, right? So what has been your experience, Rachel, in terms of these buildings?
Yeah, you know, I think it ultimately all has come down to the owner operator. And I don't mean to diminish that, because the operational requirements associated with buildings are, as you said, Ram, ultimately the most important thing that we do as designers is inform that and inform and make sure that the system operates properly. And I think there's two key points of feedback that we've received. Number one, where training has not been appropriately delivered, and I'm putting on my construction management hat a bit here, but where training has not been appropriately delivered to facilities maintenance and ongoing operations teams at facilities, those are the critical issues we come into when it comes to heat pumps and VRF technology. We recognize it's still a somewhat unfamiliar technology and still requires a lot more training than the traditional fossil fuel-based system. So absolutely, Ram, on that note, I will say training, and make sure that you as a designer, if it's a design build process or whatever process it looks like, whatever engagement you have with the owner operator, ensure that that is clarified through your design documents. The second thing that I will say on that note is where they work properly, where they are well maintained, we've seen great operational, actual like calibrated energy results. They've been super effective where they've been well maintained. We've had great feedback from different university facilities and maintenance teams where it's able to work properly. But again, I think it all comes back to that training point and making sure that the operations ensure continuity if the system is well designed.
Okay, that's good to know. I mean, it'll be, yeah, I mean, one of the things we are looking at is design guides for thermal systems, and would be great to collect all your collective experience with these systems and how it's worked out. Right? So, thank you. Yeah,
Absolutely.
Third question I just want to ask you is, what has been your experience, maybe NORR's experience too, with low GWP refrigerants? Are you seeing customers ask for systems? Are you seeing, I mean, Europe has a pretty big movement. Are you seeing that in North America?
Blake, you want to take that?
Sure, I'll jump on it. So, you know, I think a lot of clients don't know to ask that question. And I think that, you know, a lot of times we even rely on our own experience a little bit too much. And we get the luxury of being the generation that doesn't get to say, well, this is how we've done it for 30 years. So there's that. Now, with regard to the, you know, which I'll call myself out as being guilty of that for far too long, because I didn't know to ask the question. So a few years back, I started diving into the research on this just to see what it meant. And if you look up at the list at that time, I think there were 40 something various different refrigerants that you could use from. And then if you go down the list and you look, and this was spurred by my interest in lead buildings and working on lead buildings. We went down the list and found that there were 7 of those 40 something refrigerants that are compliant with the GWP, or the global warming potential of 0. And so we just started asking the questions, can we specify this? And most of the time it was yes. Sometimes we would run into, particularly on lab projects, we would run into smaller scale equipment that you couldn't specify anything but that. But again, it's really just us taking that on. Like, it's not really a cost. I'm sure there's a cost differential between one versus the other, but it's not such that in the drop of a bucket of a large building project where we would be asking those questions, that it's restricted us from being able to do it when we ask the questions. So that's why we have to ask the right questions all the time. And again, a lot of these things are just, you know, good design leadership on our own behalf, and the clients will usually follow suit, particularly when there's not a detriment to their ability to function, which we haven't found from utilizing lower GWP refrigerants.
Yeah, I'd also just add to that, in similar fashion to how I responded to Lindsay's comments earlier about just engaging sooner and having the conversations. I think that's the same is true with manufacturers, with mechanical equipment manufacturers for low GWP refrigerants. I think just if you,
and Rachel, you can probably expand upon this too. That now there is some, if I'm just going back through my memory here, because it's been a while since I've had that conversation, but there is some reticence about the long-term availability of various different refrigerant sources, just because of the way that market is shifting and how it gets managed at the end of its life. And I don't know if you can shed some light onto that, because I remember thinking like, oh, this is something interesting I would never have thought of having to think about, right? But you start asking questions, you realize the more things you don't consider.
Yeah, I don't have a direct answer to that, Blake. I will say refrigerants are not in my direct purview. However, I will say that MEP 2040, kind of their guidance related to embodied carbon related to MEP systems, including that of refrigerants, they have some great guidance. So if there's any interest in low embodied carbon refrigerants, MEP 2040 is probably what I would recommend as a baseline and a basis for what's available in the market.
I think Ram, your point about heat pumps is a really good one, and we've had a number of discussions about that. But most of it comes down to developers and building owners when you're trying to make a decision, having either experience or track record or proof that they actually work, and they actually work in your environment that they can point to. And if it's the building that you're in right now, and you ask probably the building owner than the building that you're in right now, they would probably say, we'll never use it again. And it's that kind of building owner or developer that you're trying to convince. And certainly we as architects and engineers, would, and Rachel would probably put it on the table probably every time to try to convince them. But in the end, you're sitting at that table and trying to convince a developer or a client, and it becomes a little bit difficult when the client has had a bad experience or is not knowledgeable about it and tends to go back to, as Blake said, we've done it this way for a million years, and it's tested and true, and we're going to continue doing it. That's the dilemma. And how hard do you push?
Yeah, and that's going to be a good question. I think they'll have to work on somehow getting the collective experience all pulled together and success stories, because that's going to be an important part of the transition. The concern is that if we don't have, if it becomes like a Wild West, right, where people are just putting in based on some claims and they don't operate, you're going to have concerns from the customer side or the developer side.
Ram, can you talk a little bit about certainly from the government side and policy, and how policy is affecting certainly electrification today, and certainly with the announcement yesterday from the IPCC and where we're going with not meeting our targets for net zero, and talk a little bit about certainly from your perspective, government policies and where we're going with government policies.
Yeah, I mean, we of course are going through probably a once in a lifetime moment, at least in the US, with regards to support for the technologies. Between the infrastructure law and the Inflation Reduction Act, there's huge incentives that have been put in place for technologies such as heat pumps, but also things like smart panels that can enable that transition, right? So from a policy perspective, I think there is a huge amount of incentives that are being put in place to be able to enable the transition. From the building technologies office side, we focus more on the R&D trajectory, but we do RD&D, which is research, development, demonstration, and deployment. So what our focus is really looking at part of the questions that we are asking here, right? How do these things work? How do they actually work in practice? How do you create best practice guides that can help the industry? So we are doing and we are investing in those resources that can help the market transformation. On the other side, we are also putting in place. Yes, we work with ASHRAE, for example, on 90.1. How do we advance 90.1? How do we advance the code towards getting to zero energy codes, right? But then on the other side, we also have voluntary programs like our Zero Energy Ready Homes program, which is focused on getting to zero ready, which is of course without renewables, but literally advancing the envelope on how we build not just our single family homes. Recently, we've been focused on manufactured housing. We have been focused on multifamily housing. So we are trying to get these voluntary programs and best practices out into the market so that we can enable the transition. We are also working with utilities, for example, on understanding what it means to the edge of the grid. So one of our big initiatives is actually called Connected Communities, which is looking at, it's a cohort of 10 different projects all multi-million-dollar projects. Looking at community scale, how do we go through this decarbonization transition, whether it's new construction, existing buildings. One example is we are working with Ohio State, who has a huge geothermal field on their campus, but looking at how they can use their new buildings and flexibility from their new buildings so that they don't have to expand their existing power plant. So we are investing in research, we are investing in demonstrations, we are investing in the deployment side, and all of these together helps us understand what works, what doesn't work, and that helps move policy forward in terms of standards and codes. So it's a comprehensive approach using technology to enable policy.
Thanks. I'm going to bring on Chad. Chad, do you want to come online? And Chad Menard is principal in our Detroit office. If you want to turn on your camera, Chad. Oh, there you are. Chad, you've been collecting questions from the audience. Do you have questions for Rachel or the panel?
Yeah, there is a couple questions here. So there's one question, and I think, Lindsay, you kind of touched on this a little bit. Are there situations where grid electric sources, example, dirty generation or line loss, where the grid preclude all electric buildings? Does that, stop us from actually proceeding with that because of the grid system?
Yeah, I mean, I can only speak for the service territory where I work, but we've certainly looked at some of the data around this from across the country. I think there are still pockets of the US, and I'm sorry to our Canadian colleagues, I don't really know much about Canada's fuel mix, but in most parts of the country, because of the greater efficiency of the electrification technologies, they're still going to result in greenhouse gas emissions. And that is true in where we operate in the PJM footprint in Southwestern Pennsylvania. The one thing we didn't talk about was the question of line losses. We hear that a lot in recent years in our area. There was a lot of interest in combined heat and power. So you sort of have like two sides of the coin. One is like, how do we electrify and get rid of like burning fossil fuel on site? And the other side is like, oh, it's way more efficient. Let's burn more of our natural gas that we have here at, schools and universities. Certainly there are, a lot of efficiencies of CHP where it makes sense. But because of that conversation, we kind of dug in a bit. And I know the Energy Information Administration, EIA, estimates nationwide an average line loss figure of about 5% for T&D because of the relatively urban and compact nature of the area we serve. We estimate ours to be a bit lower than that, maybe like a 3 to 4%. So again, when you're looking at the efficiencies of the projects, you're still netting out with a benefit at the end of the day to the customers, as well as in terms of greenhouse gas emissions.
And the other thing I'd add to that, from one of the first slides I shared where we had the bar charts of different state by state grid GHG emissions, David, to answer your question, moral of the story is yes. In short, it can preclude an all electric building, but the second component of that is to look at an all electric ready building, to look at on-site renewables, to look at understanding how, from a carbon perspective, opposite of what Lindsay just shared from a utility engagement perspective, from a carbon perspective, there's still ways to do better in that scenario. So I think just considering all things, policy, anticipated upcoming GHG factors, efficiency of these system selection, all of those things may preclude it, but they also may still result in an all electric building, at least one that's all electric ready.
And maybe I'll just add one comment to that too, right? Because when we look at the grid, we have to look at, if you assume the life of a building is 50 years, then you have to look at what the grid's going to be like over those 50 years. So the National Renewable Energy Labs has a tool called Cambium, which looks at long-term marginal emissions, which is factors in how the grid's going to transform in different parts of the country over the next 30 years. And when you look at that, the grid of 2040, even in an area that might be having a lot of coal power today, looks like the California grid today, for example. Right, because as a transition happens over the life of a building, you're going to save greenhouse gas emissions. So think that's something we'll have to look into.
And if I may, I'll just augment my answer briefly. And in terms to the point about line losses, Ron mentioned the work that's happening in the utility sector to have better visibility, sort of these edge of grid technologies. How do you do more with what you already have in place? And so dynamic line rating devices are one of those that we've started to implement, for as long as we've had transmission, we've basically, made assumptions about what the capacity of those lines are. Now we're starting to install sensors to actually have better real-time data. Sometimes you can push more power through than you realized. So I think all of those, we're doing similar things on the distribution side to have better real-time visibility. And I think that will also help to getting to better efficiencies, less line loss, whereas we have more distributed generation, having a better eye on how that's impacting the grid. It all plays together. Good question.
To piggyback on that too, and just to take it from kind of the scale of the utility back to buildings, generally we're doing a lot of larger buildings right now. The economics are such that the larger the building, the bigger the yield, but also it's just harder to build smaller buildings now in urban areas in particular, where most of us are practicing. And not every with the comment about on-site CHP coming back into play when we're trying to minimize combustion, I've seen a lot of projects get caught in that conundrum. And depending on where they are in their legislative metabolism, they either are obliged to this forever emissions or not. But it's easy to get bogged down in the wording and the nomenclature. And again, CHP is not an energy conservation measure. It's going to be using the energy that's produced, whether it's from diesel or CHP or from renewables. It's really a cost-saving metric, and there's also other benefits such as resiliency and redundancy that are built into those systems. So if you're working in a municipality where, for example, and I've been trying to argue this in Boston unsuccessfully, even though I've been told that we would get help on this from from various different ordinances. It hasn't come into political play yet, but if we could just start to eliminate diesel, for example, and have on-site CHP as backup power systems, that would be a huge win for global warming, just because the global warming potential of various different greenhouse gases is very different, and diesel happens to be quite high. So if we could substitute something for a technology that exists that's meeting everyone's comfort expectation levels and helps them save cost as well as provide some redundancy, then everyone is on a very different metabolism as opposed to Boston or New York. And so we're practicing in these large global practices that have footprints everywhere. We have to remember to also remember where Boston and New York was a decade ago or 20 years ago.
So there's another question from Derek. What percentage of the 40% of greenhouse gas emissions from buildings are industrial? And he goes, I'm assuming that these are the highest emitters. I would assume that heat pumps and performance envelopes would only go so far in reducing the reduction of these buildings due to their internal processes. Do the numbers that were presented take into consideration to still be mostly neutral by 50 with current trends, or do they also assume we have a cleaner grid for them to use by that time?
First of all, thank you for the question. I will be completely honest and transparent and say industrial is not explicitly addressed in the study because frankly, our firm does not do a ton of industrial based work. So I don't want to give any answers that I am not qualified to give. What I will say though, in similar fashion to some of the lab studies presented where we showed the humidification really being the peak heating load and really being a critical component of potential non-compliance in that grid resiliency section, process loads, as you mentioned, are absolutely kind of the next component of industrial facility decarbonization. I don't have experience there. I can't say any more about that, but I think you're completely and absolutely right. When we look at things in labs such as fully electrified humidification, that's a great example of that. But I will say that I know in the broader conversation about building related greenhouse gas emissions, industrial is absolutely a very large component of that puzzle. But I'd hand it to Ram or to Blake to share any more insight if you've got any on industrial buildings.
So when we look at the percentage of emissions from buildings, right, there's many definitions. Some include embodied, some don't. When we've been looking at it and from the EPA data, it comes to around industrial, transportation, and buildings are all around the mid to low 30s. So they're all kind of even. But that 32% or whatever number that we've been using doesn't include industrial, except there's some landfills, I think, are counted as part of buildings. So there's like 2% in there. But most of the emissions from buildings comes from the scope 2 emissions from the grid, because buildings are around 75% of all electricity used. So then it essentially, a lot of the big component of building emissions is from the scope 2. So long-winded answer, but the industrial component, if we are using the EPA numbers, which show buildings to be about 32%, are pretty minimal.
So
There might be some light manufacturing in there, but other than that, yeah. Mm-hmm.
So I'll add on to that to say that I have done one industrial project that's currently under construction right now. And the goal was to eliminate fossil fuel consumption on that particular site. And part of that was not tied to any green building certifications. It was a project in Vermont, which has a green grid and has a lot of incentives programs for energy efficiency. But it was more tied to the product that the industrial building itself was manufacturing, which was an all-electric vertical takeoff and land aircraft that is fully battery powered. And they manufacture the aircraft and the batteries on the site. And so they were not being driven by anything other than their desire to have a facility that generated their product that reflected the product itself, which was a really interesting proposition that we had. But the same strategies that were talked about in multifamily residential and commercial projects that were explored earlier in the presentation were at play in this particular project. So it utilizes VRF systems, ground source heat pumps. And one of the biggest opportunities in the industrial sector, irregardless of its process loads, which are difficult to pin down, particularly because we're trying to move towards automation in manufacturing, which is going to make the loads a lot bigger. And it also allows you to scale up your manufacturing capacity over time, is the fact that the rooftop and the parking areas associated with industrial areas is a huge potential to get your renewables percentage in your local municipality up. And I see it as something that's not being fully utilized. And it always boggles my mind when I see one-level buildings with no skylights and no mechanical equipment on the roof, why they're not taking advantage of solar. And there's lots of options for low weight, low cost solar and power purchase agreements now that there's really no excuse to not be utilizing it. So, even if it's not the easiest sector to predict a zero energy balance, there are all the strategies that work on the other buildings work here. And in particular, the solar is such a low hanging fruit, amazing opportunity. It just should be utilized every single time.
Chad, just one last question.
Yeah, and it's really it's a comment in my experience. So we just I've been working with Blake quite a bit. He's been really trying to educate us in Detroit and our team, and I appreciate the presentation because it was it's an engineering part of the engineering series, but it's funny, it goes back to envelope and which is more the architectural side. So we just did a feasibility study, or we're actually still working on a feasibility study for a local university for a lab building that's being rehabilitated, and it's really an educational. I mean, we really have to drive home the education behind this, because it's not just the engineers, because I think the engineers were actually doing a very good job of helping do an all-electric building. We are pushing the envelope with triple glaze system because it's a lab building. They wanted the natural light. Where we struggled was the estimators. So the estimators couldn't put in the fact that you're saving money because of your envelope in your systems, and they weren't estimating the system part because it was a feasibility study, so it's early on. And so, we had to help educate the estimators to get the estimation correct. And then not only that, we had to sell this to the facility group, and then they have to take this from the facility group and sell this to the finance people. So the amount of education that has to happen from not only Blake to me, to engineers to me, from me to the estimator, and then taking that information and then trying to get the facility people on board. Then we have to get the finance people on board. And it is such a difficult process. And it needs to come from top down and bottom up. And, you know, I know, Blake, you mentioned the whole thing with the Scottish government that's pushing the amount of funding, you know, allocated to the project based on performance. And so it's driving that top-down approach. At the same time, we're trying to do the bottom-up. So I really appreciate the presentation. I really appreciate this because it's going to help me sell this to the owners and to facilities people, and hopefully it'll get it to the finance people and get these projects on board. So, thank you.
With that, Chad, I think we've run out of time. I want to sincerely thank Lindsay for being on this panel. Blake, thanks for being on. Ram, thank you for your time. I know you're a really busy guy, and you're doing an incredible amount of effort. I mean, anyone that's in the government right now and doing the kind of effort that we really need from the policy side and the research side is incredibly important. Thank you for taking the time to be part of this panel. Rachel, that was an excellent presentation, and thank you. I mean, I can't believe how much you packed into that presentation. I think it was an incredible presentation for everyone. And I want to echo what Chad just said. It's, you know, we're architects, we're engineers, but, you know, it comes down to convincing the developers, convincing the clients, convincing the estimators, convincing that whole team that this has to happen. Like, I mean, there's no choice here. It's not, you know, we'd like to do this, we have to do this. It's it's something that we don't have any choice on, and it's we know that if we don't do this, we're not going to hit the 2030, we're not going to hit 2050, and there's some real concerns that whether or not we're going to be there, and we just don't have any choice. And the faster everybody gets on board and understands that, the better. And yes, there are costs, but you know, there are costs that we're going to have to bear, and we can't keep doing things the way that we were doing it. And when you talk about the building envelope, we can't keep building buildings that have all glass. I mean, we have to stop that. You know, punch windows are windows that you can see through in buildings, and there's nothing wrong. I mean, there was a whole era where we were doing buildings with punched windows. There's nothing wrong with those buildings. You know, doing 60-40 on buildings, those buildings are just as useful and workable as buildings that have full glass. This whole notion of building condominiums with full glass from ceiling to floor because they're easier to build has to stop. And I think that, you know, we brought up a number of things today that, you know, this discussion has to continue, and everybody needs to pour a lot more effort into this, but it's everyone at the table needs to continue this discussion. So I want to thank you all for being part of this NORR Ed, all of the clients that are on, people at NORR, and all of the students from the 14 schools of architecture that are on. I mean, you are the future, and we're certainly going to be relying on everybody to do their part in this important initiative. So thank you all for being on, and we'll see you all next time. Take care.
Thanks, everyone.
Thank you. Bye-bye.